Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 9th, 2026, about 6 days ago. It introduces a method called contact-anchored policies, which replaces abstract language instructions with precise physical contact points to outperform state-of-the-art models by 56% in zero-shot evaluations. The paper is titled, Contact-Anchored Policies, Contact Conditioning Creates Strong Robot Utility Models. And as we'll see later, the fact that it achieves this level of generalization with just 23 hours of training data is really impressive. Figure 1 illustrates the core concept. On the left, instead of using abstract language instructions, the system uses a concrete contact anchor, effectively a specific XYZ coordinate in space. The middle panel shows the robot applying this to pick, open, and close objects in new environments it hasn't seen before. Finally, the bar chart on the right highlights the massive performance jump. While the standard Pi 0.5 droid model succeeds only about 25% of the time on picking, this new method achieves 83% success on its first attempt. Well, Figure 1 sketched the general idea, but Figure 2 explains the mechanics. The top panel illustrates their hindsight contact labeling strategy. Here, the system identifies the exact frame where the gripper touches the object, then projects that 3D coordinate backward to label the trajectory. In the bottom panel, we see that during deployment, this target point comes from a user click or a vision language model. Finally, on the right, these contact tokens merge with visual data to drive the policy head, which outputs the 7-dimensional action. While Figure 2 detailed the mechanics, Figure 4 introduces EgoGym, the simulation benchmark used to refine the model. The top section illustrates how the simulation is rigorously aligned with real-world CAP data, syncing both action and observation spaces. Below this, the diagram shows how the system generates diverse procedural scenes with texture augmentations to stress test the policy. This setup allows the team to perform overfitting detection and robot calibration in simulation, identifying failure modes before any real-world deployment. So, Figure 4 established the simulation benchmark. Now Table 1 presents the hard numbers from real-world evaluations. On a stretch robot for the pick task, CAP achieves over 83% success, and adding retries pushes this to 90%, nearly doubling the any grasp baseline. What is striking is the cross-embodiment performance shown in the middle section. The policy transfers zero-shot to Franca, X-arm, and UR3E robots. Notably, on the Franca arm, CAP hits 79% success, whereas the Pi 0.5 droid model only manages 25%. Alright, while the previous table listed the internal metrics, Figure 8 validates them through independent external testing. The top set of bars confirms the strong internal performance we just saw, with the Stretch and X-arm robots both hitting 83% success. But remarkably, the bottom section shows results from external collaborators who ran the same checkpoints in their own labs. Even in these new settings, the policy holds up, scoring 88% on the Stretch and 79% on the X-arm, which proves the method is robust across different physical sites. So, Figure 8 confirmed the robust performance of individual skills. Now Figure 9 shows how they combine into long-horizon behaviors. The top row illustrates a coffee retrieval task, where a high-level VLM controller sequences atomic, contact-anchored policies like open, pick, and close to fetch a bag of beans from a cabinet. In the bottom row, the system tackles a table cleanup task, repeatedly invoking the pick policy to clear multiple objects into a bin. This demonstrates that these modular utility models can effectively serve as tools for a larger intelligent system. Well, Figure 9 showed the final results, but Figure 10 reveals the iterative process behind them. The left chart plots the correlation between simulation scores and real-world success rates. The data points hug the diagonal line tightly, proving that gains in the EgoGym simulator reliably predict better performance on physical hardware. Then, the right panel breaks down this progress across 4 model iterations. Starting with just 20% success in version A, the team analyzed specific failures like empty grasps, shown in red, to refine their pipeline, eventually climbing to 80% success in version D. Wrapping up, 2 key takeaways stand out. First, conditioning policies on explicit contact points is far more effective for manipulation than using language alone. Second, this method achieves robust zero-shot generalization with only 23 hours of data, challenging the assumption that we need massive resources to build generalist robots. The results suggest that smarter, modular utility models can outperform sheer scale. That's it for this episode of the AI Research Roundup. I'm Alex, thanks for listening.